really talk about the movement of particles and the various mechanisms of transport. Okay, so we'll start with these two objectives. Identify the three factors that influence the rate at which substances are moved across the membrane passively, right? We really want to stress that movement is happening passively, although it's not, some of these mechanisms are not going directly through the membrane. They require some help. This is still passive, so this is still happening according to a concentration gradient and does not require energy, okay? And then our second objective is to talk about the four factors that affect the permeability of membranes and explain how and why the permeability will be affected. Okay, so we'll talk about the mechanisms of transport and then the factors that affect permeability. Now, when we look at transport across the membrane, we have the movement of particles to bring the concentrations to diffusional equilibrium. This is a state where we have the net concentration of both of our solutions being the same across that membrane. So in this top image, we can see that this is at diffusional equilibrium. We have side 1 having the same concentration, 1 molar, versus side 2 having the exact same amount of solids dissolved in the solution. And so although we have slight movement of particles from one side to the other, right, we still see one-way flux in both directions. We have no net movement because we have no what? We have no what in terms of our solutes and the concentration. Excellent. So we don't have an uneven distribution, meaning we don't have a gradient, right? We have no concentration gradient, so we have no net movement, right? In the bottom, we have a higher concentration on side 1 and a lower concentration on side 2. And so here we have a gradient. And so again, once we see, we are still seeing net movement from one side to the other, but the net flux is from high concentration to low concentration. Right, so we still see one-way flux going in both directions, but the overall movement will be from high to low concentration. So we're going to speak about the actual mechanisms of passive transport, which are simple diffusion, facilitated diffusion, and diffusion through channels. But we just want to remind ourselves here that passive transport is spontaneous, it is downhill, and it does not require energy. Rather, it liberates some energy. So we can see that it is an exergonic reaction in that way, or exothermic in that way. So simple diffusion is the first mechanism we'll look at, and this is characterized by the fact that particles are moving directly through the lipid bilayer. So we talked about the structure of the lipid bilayer, that phospholipid layer, and particles that can go right through that lipid bilayer do not need any type of carrier, do not need any type of channel. They are simply diffusing across the membrane. It's the first mechanism of diffusion. So let's talk about some of the factors that affect the diffusion rate. The first one is going to be the magnitude of the driving force. So how much of a gradient do we have? If we have lots of particles on one side and almost no particles on the other side, we have a really big gradient, we have a really strong driving force. If we have sort of almost equal amounts of particles on either side, and we have a minimal or a small gradient, then we have a small driving force. So the strength of the driving force will determine the rate of movement. The other factor is the membrane surface area, and we'll talk more about some examples. But if we have more area, more surface area exposed for particles to move through, we're going to have a faster rate of movement. Likewise, the permeability of the membrane dictates the rate as well. So if you have a membrane that is not permeable to our solute, our rate is 0. And if we have a membrane that is very permeable to our solute, we have a much higher or faster rate. Okay. So let's illustrate here the magnitude of the driving force. Okay, so factors affecting the rate of simple diffusion. We said one is the magnitude of the driving force. Two is going to be the surface area exposed. And then three is going to be the permeability of the membrane. Okay, so let's look more closely at what the magnitude really means, the magnitude of the driving force. So we'll look at three different scenarios here. We'll call them A, B, and C. Now we have a container that's separated by this permeable membrane in each of our little scenarios here, and we have differing solute concentrations on either side. And then here, okay, so we have 1 mole on this side and then 0 moles on that side, right? So no solutes dissolved on that side. We have 0.8 on this side, 0.5 on that side. So almost equal concentrations for scenario B. And then for scenario C, we have exactly equal concentrations on both sides. So who can predict what our rates will look like in each of these? Who can predict where we'll have the fastest rate versus the slowest rate? So which of these scenarios will we see a fast rate of simple diffusion? Scenario A, yeah. So in scenario A, we're going to see a strong chemical driving force, which equals a faster rate of movement. Okay. In scenario B, we're going to see a medium driving force, which equals a medium rate. And then obviously in scenario C, because we have equal solute concentrations, we have no we have no net movement, we do have one-way flux, okay? So whereas here we have a strong movement this way, here we have a weak movement this way, here we can see that there is some movement back and forth, but no net movement, right? So there's no driving force. So we have no net force. Right, so our rate of movement equals 0. And just to remind ourselves here, we can say that this scenario is at diffusional equilibrium. Okay, we're at diffusional equilibrium in that last scenario. Okay, so this is what we speak about when we talk about the magnitude of the driving force, the strength of that gradient, right? The strength of the separation. The second factor has to do with the surface area exposed. So if in this first scenario, we extended the membrane, so we have the membrane here, if we extended the membrane and we had more surface area exposed, we would have a faster rate. Alternatively, if we decrease the membrane, right, let's say we cut the membrane down or made the container smaller, we would have a slower rate. So the amount of surface area that's exposed for exchange of materials will dictate the rate of movement of particles from side to the other. And then lastly, the permeability of the membrane. So how likely are these particles to go through the membrane? And that is going to depend on a few other factors that we'll talk about, such as the size and charge and shape. But basically, if we have no permeability, we have no movement, even if we have a concentration gradient. Really important to make that point. So we can have a strong driving force, we can have a lot of surface area, but if the membrane in question is not permeable to the solute in question, then the rate is still 0, okay?